In this video we're going to look at how to sum a geometric progression. And remember, a geometric progression is a sequence that starts at a certain value a, and then each step we multiply it by r again and again. And here I'm going to assume it's a finite geometric progression that's going to stop at some point, so the last term is the nth term, which has ar to the n minus 1. We've multiplied a by r n minus 1 times. So to prove the sum of this geometric progression, let's call the sum, let's just call it Sn. That means the sum up to n terms here. So that's just adding all of these terms together, and so all the way up to ar to the n minus 1. Now let's also think about what r times Sn would be. So I'm going to multiply each term by r. So a becomes ar is ar squared, this one is ar cubed, I get ar to the 4, and the final term, ar to the n minus 1 times another r, is ar to the n. So if we call this, let's call this line 1 and this one line 2, what I'm going to do now is take the first one and subtract the second one, like simultaneous equations. So I'm going to say, well, if this is Sn and this is r times Sn, well, 1 minus 2, that would be Sn minus r times Sn. And now I'm going to do line 1 minus line 2. So let's see what happens there. Well, I take a in the line 1, and then I add ar, add all of these things, but I'm going to subtract all of these things. So I'm going to do a plus ar, but then I'm going to have minus ar from the second line. I'm going to have plus ar squared, but then minus ar squared in the next line. And you can see that all of those terms are going to cancel out in the middle here, because I'm going to be adding them here and subtracting them here. And we keep doing that until we get to the end. And so here I add, at the end I'm going to add ar to the n minus 1, and now in here before the ar to the n term there would be a ar to the n minus 1 that we're subtracting, and at the end I've also got to subtract this term here that doesn't cancel out with anything, minus ar to the n. So actually all of these ones have cancelled out, and I'm just left with a minus ar to the n. So let's factorise each side here. I've got Sn times 1 minus r, and on the other side here I could write this as a times 1 minus r to the n. So to get my formula for Sn, I just now divide both sides by 1 minus r. So I'm going to have Sn equals a times 1 minus r to the n divided by 1 minus r. And that's a formula that I could use to add up the first n terms of a geometric progression, as long as I just know what the first term is, the common ratio, and how many terms I want to add up. Okay, so here's an example. To use this, I want to find the sum of the first 8 terms of 2, 6, 18, 54, etc. So first we notice this is a GP. It's got a equals 3, the common ratio r, a is 2, the first term is 2, and the common ratio r is 3 because I'm multiplying by 3 each time, and n is 8 because I want the first 8 terms. So I just need to plug all of these numbers into the formula here to get that the sum of the first 8 terms, S8, that's 2 times 1 minus r to the n, so that's 1 minus 3 to the 8, all divided by 1 minus 3. And well, at this point I'll use the calculator, and we'll say, okay, let's do 1 minus 3 to the 8, that's minus 6,650, and times it by 2, and that's, so I've got minus 13120, all divided by 1 minus 3, which obviously is minus 2, so I want to do 13120 divided by 2, the minus 1's cancelling out, and I'll get 6,560. Much quicker than working all the terms out individually and adding them together. One thing you notice here in this form of the thing, we ended up with a minus number and a minus number, which eventually cancels out. we could write this formula slightly differently so that we only have positive values in there. If I multiply top and bottom of this by -1, I get Sn equals a times r to the n minus 1 all over r minus 1. So I multiply top and bottom by -1. So if that's confusing, don't worry too much. These things will always evaluate to exactly the same number for the same values of a, r, and n. But using it this way around, if you've got r bigger than 1 here, it's going to make them come out as positive. But they're just as good as each other. If we had a sequence where r is less than 1, these ones would come out negative and these ones would come out positive. So choose whichever one you want. In fact, let's do one with r smaller than 1. This is a geometric regression with, here I've got the first term is 1, I've got the common ratio is 1/2. You can see it just dividing by 2 each time, and this time I want the first 10 terms. So in fact, this original formula here will have the top and bottom positive, so let me use that one. As I say, either will be fine. So the sum of the first 10 terms here, that's a, which is 1, times 1 minus r to the n, so 1 minus 1/2 to the 10, all divided by 1 minus 1/2. So obviously this 1 is just 1 times it, so we don't need that. 1 minus 1/2, that's just 1/2. So let's plug that into the calculator. 1 minus 1/2 to the power of 10 on the top there, and then we divide that by 1/2, and that gives us 1023 over 512, which actually is very, as you can see, is very close to 2. 2 would be 1024 over 512. You can see actually if we keep adding these terms together, they're getting closer and closer to 2 in the sum. So that answer is as we would expect. In another video we'll look at how to sum an infinite geometric progression. In a case like this, if we kept going on forever, we would get to 2. But for now, that's the sum of a formula for a finite number of terms in a geometric progression.